So dear students, we are now moving on to the conceptual problems by Michael. So very important things, before doing up the problem, we must know how to do the problems in a conceptual way. Let us get into the problem, then we can explain the things.
Welcome to iLecture Online. And the new segment here that we're going to be talking about is magnetic fields generated or caused by moving charges and currents. We're going to start out by looking at a moving charge and trying to figure out the magnetic field nearby that moving charge. And in our example that we have here, we can see that we have an alpha particle moving to the right, and an alpha particle is basically the nucleus of a helium atom, which means it has 2 protons embedded within it. It's moving to the right at 5,000 meters per second, and they're asking to find the magnetic field at a point 2 centimeters away and directly above the moving alpha particle. So let's make a drawing of that, a sketch of that. So we have the alpha particle, which is basically 2 protons embedded with 2 neutrons in a nucleus, an atomic nucleus, and it's moving to the right at a velocity equal to 5,000 meters per second. And of course, since that's a vector quantity, we have to indicate the direction like that with the x unit vector. Now, we want to know the magnetic field direction and the strength, the magnitude of that field, 2 centimeters directly above the alpha particle. So let's say right there at a distance of 2 centimeters above the particle. And of course, as the particle is moving, that position will move along with the particle. We want to know what the field is directly above the particle that's moving to the right. And so we can draw a unit vector to that position right there. So this is our not unit vector, but I should say position vector. That's the vector that points from the particle to the position of interest. So it's called the position vector. And then the unit vector in that direction can be considered right here. The unit vector in that direction, we'll call that r with a little hat on it. Okay, now to find the magnetic field at that location, first for the direction, we can use a right-hand rule. Take your thumb, point in the direction of motion of the charged particle, and your fingers will curl in the direction of the magnetic field. And what we mean with that is that the magnetic field is pointing all the way around, like a circular loop around the moving particle. As the moving particle moves to the right, we have the magnetic field that's directed around the particle the way the fingers are curling. So looking from behind, it would be in a clockwise direction. So if the particle is moving this way, the field would have a clockwise direction. The particle moving this way, it has a clockwise direction looking from behind. Which means that above the particle, the B field, the magnetic field, will be pointing outside the board or out of the board. So we can indicate that by a little dot with a circle around it, indicating that the B field is coming out of the board at that location. Below the particle, the magnetic field would be in the board. In front of the particle, the magnetic field would be down. Behind the particle, the magnetic field would be up. So you can see how it's directed in a circular loop around the moving particle. All right, so that gives us the direction. Now for the magnitude. Well, first of all, the equation that we need to use to find the magnetic field, that is equal to mu sub naught divided by 4 pi times the size of the charge of the particle times the cross product of the particle's velocity v crossed with the unit vector in the direction of the point of interest and divided by the magnitude of the position vector squared. Now, since we're only interested in the magnitude of the magnetic field, we could then say that the magnitude of that is equal to mu sub naught divided by 4 pi times the charge q, and v cross r can be written in terms of magnitude as the magnitude of v times the magnitude of the unit vector, which is 1, times the sine of the angle between the 2 vectors, and then divide by r squared. Now notice that the position of the point of interest and the motion of the particle, the angle between them, theta, is equal to 90 degrees. And of course, the sine of 90 degrees is 1. So in this case, we have the maximum magnetic field directly to the side. And as the position vector changes direction and the angle becomes smaller, the magnitude of the magnetic field will become weaker. All right, plugging in the numbers that we have, mu sub naught is equal to 4 pi times 10 to the minus 7 Tesla meter per amp. We multiply the times the charge of the nucleus, and that would be 2 times the charge of a single proton, which is 1.6 times 10 to the minus 19. and the velocity v, which is 5,000 meters per second, and the sine of 90 degrees is equal to 1, and divide the whole thing by, we still have a 4 pi in the denominator, and then we have the distance squared. The distance would be 2 centimeters, so that would be 0.2 meters, and we have to square that. And now we're ready with a calculator to figure out what that is equal to. All right, maybe before we do that, we can see here that the 4 pi here cancels out those 4 pi, makes it a little bit easier. All right, so now with my calculator, let me figure out what this is equal to. 1 e to the 7 minus times 2 times 1.6 e to the 19 minus times 5,000 equals, and divide that by 0.02 squared equals, and we come out to 4 times 10 to the minus 19 Teslas. And just to make sure that we have our units correct, let's see what the units are. Now here, this is coulombs, meters per second, so putting the units to the right here, we have Teslas times meters divided by amps. We multiply that times coulombs, multiply that times meters per second, and then divide by meters squared. Okay, so first of all, we have a meters times the meters in the numerator and the meters squared in the denominator, so that cancels out. All right, now next, an amp is a coulomb per second, so we can replace this by a coulomb per second. And then notice that we have a coulomb in the numerator and a coulomb in the denominator. That will cancel. And then notice that we have a second in the denominator and a 1/2 in the denominator. That will cancel as well. And so we're left with Teslas. So our answer here is correct. And quickly recapping, we have a particle moving to the right. It has 2 positive charges, 2 protons. To find the direction of the magnetic
ஒரு ஆல்பா பார்ட்டிக்கல் 5000 மீட்டர் per செகண்ட் அப்படின்ற எக்ஸ் டைரக்ஷன்ல நகர்றப்போ அதுலேருந்து நம்ம என்ன செய்யறோம்னாக்க 2 சென்டிமீட்டர் அவே ஜஸ்ட் above the ஆல்பா பார்ட்டிக்கல்ல மேக்னெட்டிக் ஃபீல்ட் என்னன்னு பார்க்கணும். முதல்ல ரைட் ஹேண்ட் பாம் ரூல் யூஸ் பண்ணி என்ன செய்யறோம்னாக்க மேக்னெட்டிக் ஃபீல்ட் டைரக்ஷன் வந்து எமர்ஜிங் அவுட் இருக்கிறத முதல்ல கண்டுபிடிக்கிறோம். நம்பர் 2, ஃபார்முலா அப்ளை பண்றோம். பையர்ட்ஸ் லாவினுடைய சார்ஜுக்கான ஃபார்முலா அப்ளை பண்ணீங்கன்னாக்க μ0/4π q into b cross r. r is called the position vector. கால்குலேட் பண்ணி சப்ஸ்டிடியூட் பண்ண ஆன்சர் வந்துருது. யூனிட் சரியா இருக்கிறது, கன்வர்ஷன் சரியா இருக்கிறது பார்க்கணும். இப்போ 2 விஷயம், 2 சென்டிமீட்டர் அப்படின்னாக்க 0.02 meter வரும். 0.02 meter will be the answer.
magnetic field that it causes, use your right hand, point your thumb in the direction of motion, your fingers will curl in the direction of the magnetic field coming out of the board. Then to find the magnitude of that, we use this equation that tells us the magnetic field as a result of a moving charge. Here's our constant, here's the charge, twice the charge of a single proton, the velocity, and then the length of the unit vector, which is 1, and then times the sine of the angle between them, which in this case 90 degrees, sine of 90 degrees is 1, and then divide by 4 pi, and divide by the distance, and realizing here, of course, that 2 centimeters is actually 0.02 meters, and that's, you got to be careful. I put the correct value in my calculator, but I didn't write the correct value here on the board, and that will then give us the answer right there. Okay, that's how you do that.
அப்போ ரெண்டாவது ப்ராப்ளம் போடலாம்.
Welcome to iLecture Online, and here's our second example, how we find the magnetic field caused by a moving charge. Again, just like in the first example, we have an alpha particle that's moving to the right at 5,000 meters per second, and we're supposed to find the magnetic field located 10 centimeters away, but this time it's at an angle directed 45 degrees above the positive x-axis. So let's make a drawing of that and see what it looks like. So first of all, an alpha particle is something that has 2 protons and 2 neutrons. It's essentially the nucleus of a helium atom. It's moving to the right at a velocity v equal to 5,000 meters per second. And that's in the x direction because that's a vector quantity. And let's see now, we're supposed to find a magnetic field 10 centimeters away. So let's draw a little circle around the moving particle. with a radius of 10 centimeters. And we're supposed to find the magnetic field at a position on that circle at an angle of 45 degrees above the horizontal. So if this is the position vector r, then this here is theta equal to 45 degrees, and we're supposed to find the magnetic field right at that spot. Well, first of all, to find the direction of the magnetic field is fairly straightforward. We use our right-hand rule because it's a positive charge that's moving. We point our thumb in the direction of the moving charge, and then our fingers curl in the direction of the B field, the magnetic field. You can see the magnetic field loops around the moving charge as it's moving in this direction, and so at the very above the moving charge, the B field is in this direction, so it would be coming out of the board. Here it's down, here it's into the board, and on the back side of the moving charge, it's upward. So, assuming that directly above the moving charge at an angle of 45 degrees above the horizontal axis, we can say that the B field is out of the board. So we draw a little dot with a little circle around it, indicating that's the tip of the arrow of the magnetic field coming out of the board. All right, now for the magnitude. We need the equation that the B field is equal to mu sub naught divided by 4 pi times the size of the charge times the vector product of the velocity and the unit directional vector of the pointing vector or the position vector. And we divide that by, let's see here, the length or the magnitude of the position vector squared. Okay, that's the equation. Now, since we already know the direction of the magnetic field, we can simply then go look for the magnitude of this field, which is equal to mu sub naught divided by 4 pi times the size of the charge, and V cross R is the same as V times R times the sine of the angle between them. Now, this is the unit vector, so let me just put in a 1, because the length of a unit vector is simply 1 times the sine of 45 degrees, and divide that by the length of the position vector squared. Okay, now we can go ahead and plug in the values. So this is equal to 4 pi times 10 to the minus 7. That's Teslas meters per amps. We multiply that times the velocity. So we have, I forgot the charge. No, we need to put in the charge. And there's 2 positive charges. That's 2 times the size of one charge, 1.6 times 10 to the minus 19 coulombs. Can't forget the charge. Times the velocity, which is 5,000 meters per second, times 1, and times the sine of 45 degrees, which is about 0.707, and take the whole thing and divide it by the length of the position vector squared. The length is 10 centimeters, and so that would be 0.1 meters squared. All right, now let's find the value of that. Let's grab our calculator here. I think I'm still missing a 4 pi here, so I better put that in there. There's the 4 pi, can't forget about that. And now when we simplify things, this 4 pi cancels out that 4 pi. And let's work out the rest. 1 e to the 7 minus times 2 times 1.6 e to the 19 minus times 5,000 equals, and divide that by 0.1 squared equals, and, don't forget this 0.707, so times 45 degrees, the sine of that equals, and we get 1.13 times 10 to the minus 20 Teslas. So how do I know that's Teslas? Well, let's work out the units. If we grab all the units out here, we have Teslas times meter per amp. We have a coulomb here. We have a meters per second. And then in the denominator, we have meters squared. All right, so unit-wise, these 2 meters cancel out those 2 meters. Now an amp, that's a coulomb per second. So we can replace this by a coulomb per second. And then you can see that this coulomb cancels out this coulomb, and the 1/2 cancels out this second right here. And we do indeed end up with Teslas, which is the unit for magnetic fields. So that works out. I'll leave that on.
அப்போ போன சம்ல பர்பெண்டிகுலரா மூவ் பண்ணுச்சு, இப்போ 45 டிகிரி இன்க்ளைண்டா மூவ் பண்ணுது. அப்போ பையட்-சாவர்ட்ஸ் லாவுடைய சார்ஜுக்கான ஃபார்முலா Q into V cross R cap. R capன்றது பொசிஷனல் வெக்டர். சப்ஸ்டிட்யூட் பண்ண ஆன்சர் வந்துருது, அவ்வளவுதான்.
Welcome to our lecture online, and here's an additional problem, an additional example of how to find the magnetic field with moving charges. Now, if you look at this, you recognize this was the end where we ended up with our previous example, but what I'm adding to it now is at the same time that we have an alpha particle moving to the right, we have an electron moving to the left, and assume that at this very moment, the two particles pass one another. At the very moment that they're at the same location, what is now the magnetic field in this direction? So now it's going to be an addition, a vector addition of the magnetic field caused by the alpha particle and the magnetic field caused by the electron moving the opposite direction. So since we already found the direction and the magnitude of the magnetic field caused by the alpha particle, let's now find the direction and the magnitude of the magnetic field caused by the electron moving in the opposite direction. Since it's a negatively charged particle, to find the direction we use our left hand instead of the right hand. You point the thumb in the direction of the motion of the particle, which is this way, and then your fingers will curl in the direction of the magnetic field. And notice that over here, the field will also be out of the board, same direction as the direction caused by the alpha particle. So even though the electrons move in the opposite direction, since it's negative, that kind of negates that, and you still have an additional amount of B field coming out of the board caused by the electron. What about the magnitude of that B field? Well, it turns out that we use the very same equation. The B field is equal to 4 pi. Oh, not 4 pi, it's mu sub naught divided by 4 pi. So mu sub naught divided by 4 pi times the charge of that particle times the velocity of that particle multiplied or crossed with the unit vector pointing in that direction divided by the magnitude of that unit vector squared. So now you will notice that just about everything is the same as before. So this is equal to 4 pi times 10 to the minus 7 Tesla meters per amps multiplied times a single charge. Now you don't care if it's a positive or a negative charge because we already took care of the magnitude. So we're simply finding the magnitude of that quantity. So let me indicate here that we're just simply finding the magnitude, and therefore we don't care about the sign. Now, if we weren't finding the magnitude in this way, and we had to find it that way, we do indeed have to keep the negative sign there. But in this case, we have a single 1.6 times 10 to the minus 19 coulomb charge. So we don't care about the negative. The velocity here would be 5,000 meters per second. Again, we know that it's to the left, but we don't care about that because we're simply finding the magnitude, 5,000 meters per second, times the magnitude of the unit vector, and don't forget, then we have to multiply that times the sine of the angle, the sine of 45 degrees, and the whole thing divided by 4 pi, 4 pi, that's right, the 4 pi from there, and the distance, which still would be 10 centimeters or 0.1 meter quantity squared. And so that means that we'll end up with half the value of this right there. So we take that value divided by 2. And so this is equal to 0.566 times 10 to the minus 20 Teslas. All right. And so then the total magnetic field, and I'll use the red for that. So the magnitude B total is simply equal to the B field caused by the alpha particle. So the B field caused by the alpha particle plus the B field caused by the electron. So we're simply adding these together. Since they're pointing in the same direction, we can simply add. And the result then is, this is equal to 1.13 times 10 to the minus 20 Teslas plus let's round it off to two significant figures, 5.7 times 10 to the minus 20 Teslas. So when we add the two together, that gives us 1.70 times 10 to the minus 20 Tesla. So notice that if the magnetic field is caused by multiple particles, we do have to do a vector addition at that location. Welcome to our lecture online, and here's an additional problem, an additional example of how to find the magnetic field.
இப்போ மூணாவது டைப் ஆஃப் ப்ராப்ளத்துல முதல்ல ரைட் ஆங்கிள் போச்சு, 45 டிகிரில போச்சு. இப்போ என்ன செய்யறோம்னா ரெண்டாவது ஒரு பார்ட்டிகல் இன்ட்ரோடியூஸ் பண்றோம். ஆல்பா பார்ட்டிகல் பிளஸ் எக்ஸ் டைரக்ஷன்ல போச்சுன்னா, ஒரு எலக்ட்ரான் மைனஸ் எக்ஸ் டைரக்ஷன்ல போச்சுனாக்க நெட் ரிசல்டன்ட் ஃபீல்ட் இருக்குன்னாக்க ரெண்டு ஃபீல்டையும் தனித்தனியா கண்டுபிடிச்சிட்டு ரெண்டும் ஒரே டைரக்ஷன்ல எமர்ஜிங் அவுட்டா இருந்ததுன்னா வெக்டர் அடிஷன் போடுறோம். ஒன்னு எமர்ஜிங் அவுட் ஒன்னு என்டரிங் இன் இருந்ததுனாக்க B1 minus B2 போடுறோம். அவ்வளவுதான், ஒண்ணுமே இல்லை.
Welcome to iLecture Online, and here's the next segment in how we figure out the magnetic fields caused by moving charges in line segments. Now in this particular case, we're going to go and figure it out from a small line segment. So how much of magnetic field is caused by a single little piece of a wire carrying a current of 10 amps, 20 centimeters away from that line segment and 5 centimeters above the wire. So let's draw this out so we can see what it looks like. Here we have a current carrying wire. Let's say that current is moving from left to right. I equals 10 amps as given. We now consider a small little segment on that wire, and let's say that it has a length DL, a small little line segment with length DL. And DL, let's say that's equal to 1 millimeter long. And we want to find the magnetic field at a position 20 centimeters in front and 5 centimeters away from the wire. So let's say that this distance right here is 5 centimeters. And let's say that this distance from there to there is equal to 20 centimeters. And so what is the magnetic field equal to at that location? All right. So the first thing we're going to do is find the direction of the magnetic field, because that's relatively easy. Since the current is moving from left to right, and it's positive current, at least to be assumed, then we know that we use our right hand rule. We point our thumb in the direction of the current, our fingers will point in the direction of the magnetic field, and it looks like at that location, magnetic field is coming out of the board. So let's indicate that like so. So here we have a magnetic field coming out of the board. We indicate that by the tip of an arrow. Now what about the magnitude of that field? Well, starting out with the equation that we use for single point charges, we can say that the magnetic field B is equal to mu sub naught divided by 4 pi times the size of the charge multiplied times the velocity cross B. Oh, not cross B, I'm sorry. That's the velocity cross the unit vector R divided by R squared. So now we're not given the velocity of the charges. We're not given the size of the charge. We're simply said it's a section of dl. So we have to convert that equation. How much charge is being carried by this? How do we figure that out? So let's take this portion of the equation right here. So we're going to take this part of the equation and we're going to show you how to adapt that for our particular problem right here. So we end up with Q times V cross R, like so. Now Q is charge, and how does that relate it to I? By definition, I is equal to charge per unit time dt. So if we change this like so, if we say, well, Q times V, and V can be written as distance over time, like so. And of course, distance is still a unit vector, cross R. And then we move the dt underneath here. We can say that this is equal to Q divided by dt times x cross R. Now we can say that Q times dt is the same as the current running through the wire. So this can now be written as the current I. And let me move out of the way so you can see that. So I move the dt underneath here. Now this is equal to the current I times x cross R. Okay, now, I move this around. This should be the x cross R. Now, this here is caused by this line segment right here. So instead of writing x, we're going to write dl because it's really this little segment that we're interested in. So this is equal to I times dl cross R. So that's unit vector. And now we can go ahead and replace what we have up here by this quantity right here. So this can now be written as mu sub naught over 4 pi times, instead of Q V cross R, we're going to write I times dl cross R divided by R squared. Now everything else is still the same. This is still the unit vector in the direction to the point of interest from the part that's causing this magnetic field. So if we draw the r vector right here, this is the position vector r, and this here is the unit vector r, like so. And now if we, and of course this is a little line segment dl, if we now cross dl cross r, we get the length of dl times the length of r times the sine of the angle between them. So we need to find theta. So now this can be written as, this is the B field. If we now find the magnitude of B, this is equal to mu sub naught divided by 4 pi times the current times the length dl times the length of the unit vector r, which is 1, times the sine of the angle between them, theta, all divided by the length r squared. All right. Now we're given the length dl, it's very small, and as long as dl is small compared to the distance away from this line segment, we can go ahead and make that substitution. We need to find the angle theta, and we need to find the distance r. Now since this is a triangle right here, we can use Pythagorean Theorem. We can say that r is equal to the square root of the sum of the squares of the sides. So this here is 20 centimeters. We can square that, plus this here is 5 centimeters. And that will give us the length of r. If we then square r, that means this is squared. We'll take out the radical. Okay, so we have r. Now we still need to find theta. Theta, by definition, can be found by taking the arc sine, or maybe the arc tangent. That would even be better because we're given the opposite side and we're given the adjacent side. So we can say that theta is equal to the arc tangent of the opposite side divided by the adjacent side. So in this case, that's equal to the arc tangent of the opposite side, which is 5 centimeters, divided by the adjacent side, which is 20 centimeters. So what is that angle? Let's find it out. So we have 5 divided by 20, and take the arc tangent of that, and so that is 14 degrees. So we know that theta is 14 degrees, and we can find r. So we have 20, we square that, plus 5, square that, add them together, take the square root, and it's 20.6. So r is equal to 20.6 centimeters. Plug in those numbers in our equation right here. This is equal to 4 pi times 10 to the minus 7 Tesla meters per amps times the current in the wire, which is 10 amps, times the line segment dl. It is 1 millimeter in length, of course. We have to convert that to meters. That would become 0.001 meters times 1 times the sine of 14 degrees. And take the whole thing and divide it by 4 pi times the distance, which we said was 20.6 centimeters. That becomes 0.206 meters, and we have to square that. And notice unit-wise, amps cancel out. Meters times meters and meters squared cancel out, and we end up with Tesla. So units is okay. Now, working out the rest, we can already cancel the 4 pi and the 4 pi. So we have 1 e to the 7 minus times 10 amps times 0.001 times the sine of 14 divided by 0.206 squared equals, and the magnetic field caused by that little line segment is equal to 5.7 times 10 to the minus 9 Teslas. So here you can see we have the magnitude of the magnetic field and the direction of the magnetic field. So recapping.
இப்போ என்ன கொடுத்திருக்காங்கனாக்க ஒரு கரண்ட் கேரிங் கண்டக்டருடைய ஒரு செக்மெண்ட் லெங்த் கொடுத்திருக்காங்க. ஒரு லாங் செக்மெண்ட்ல 1 மில்லிமீட்டர் லெங்த் இருக்கக்கூடிய ஒரு கரண்ட் எலிமெண்ட் எடுத்துட்டு அதுல 10 ஆம்பியர் போறப்போ அதுக்கு முன்னாடி 20 சென்டிமீட்டர் தொலைவில், அதாவது 5 சென்டி, அதாவது find the magnetic field created by a 1 millimeter long segment of a wire carrying a current of 10 ampere 20 centimeter in front of the line segment and 5 centimeter above the wire கொடுத்திருக்காங்க. R is equal to 20 centimeter கொடுத்திருக்காங்க. ஒயருக்கு மேல 5 சென்டிமீட்டர்னு கொடுத்திருக்காங்க. இப்போ ஏற்கனவே பையர்-சாவர்ட்ஸ்-லால Q into V cross R என்ற ஃபார்முலாவை ஐடியல் கிராஸ் ஆர் பை ஆர் ஸ்கொயர்ன்ற ஒரு வெக்டர் ஃபார்முக்கு கரண்ட் ரிலேட்டட் ஃபார்முக்கு மாத்திக்கிறோம். நமக்கு ஏற்கனவே தெரியும் 3 ஃபார்ம் பார்த்தோம். கரண்ட் டென்சிட்டி, ஐடியல், Q into V cross R, இந்த 3 வடிவங்கள் நம்ம ஏற்கனவே பார்த்தோம். இந்த ஐடியல் கிராஸ் ஆர்ல என்ன பண்றோம் அப்படின்னாக்க, நம்ம இந்த ஆர் வெக்டருடைய வேல்யூ வந்து ஏற்கனவே கொடுத்துருக்காத 20.6 ஏற்கனவே நம்ம கால்குலேட் பண்றோம். ஆனா உண்மையா அவங்க 20 சென்டிமீட்டர் கொடுத்துருக்காங்க. நம்ம கொடுத்துருக்கக்கூடிய வேல்யூஸ்ல நம்ம என்ன பண்றோம் அப்படின்னாக்க, வேல்யூஸை சப்ஸ்டிடியூட் பண்ண ஆன்சர் வந்து I is equal to கரண்ட் எவ்வளவு 10 ஆம்பியர். ஓகே, டிஎல் எவ்வளவு 1 மில்லிமீட்டர். சைன் வேல்யூவை இங்கிருந்து கண்டுபிடிச்சு போடுறோம். அது வந்து 14 டிகிரி வருது. அதுக்கப்புறம் இந்த ஆர் வேல்யூவும் ட்ரையாங்கிள் இருந்து கண்டுபிடிச்சு மேக்னிடியூடும் டைரக்ஷனும் கண்டுபிடிக்கும். ரொம்ப சிம்பிள்.
Welcome to iLecture Online, and here's another example of how to find a magnetic field, in this case due to a current carrying wire. So let's read the problem. It says, find the magnetic field at a point a distance r away from a wire of length 2a carrying a current I. The point is directly across the midpoint of the wire, which will make the problem a little bit easier to do. So here's our current carrying wire. The length of the wire is 2a. Here's the midpoint. So distance from there to there is a. The distance from there to there is a. Let's see here. We have the point of interest right here, a distance r away from the wire, and directly across from the midpoint. And so the question then is, what is the magnetic field equal to over here? And of course, we have a current carrying wire, so let's say there's a current I that long, of that value right here, in that direction. Now, the wire is not infinitely long. There's only a limited amount of wire here. We don't know what happens above that, below that. We're only considering the contribution of the current in this segment of the wire at this location. So how do we do that? Well, we can see that different pieces of the wire will have different contributions over here, and the amount of the contribution will diminish as the angle gets larger and we're farther away from this point. So this looks like something we're going to need to use integration for. So to do that, we're going to take a small little segment right here. Let's say that the direction in the vertical direction here is y, and the line segment that we're considering here is a distance y away from the midpoint right there. And the length of this little segment, let's call it a little dy. So the length of that little segment is dy. And that segment will be a distance r away from the point of interest, so let's call this r. This distance from there to there is big R, and this distance right there is y. And right away you can see the relationship between r, y, and big R. You can say that little r right there, the hypotenuse, is equal to the square root of r squared plus y squared. All right, now, how much does this little line segment contribute to the magnetic field over there? Well, let's use the equation that we used before for a single point charge that says that the magnetic field B is caused by 0 mu sub naught divided by 4 pi times the charge that causes the magnetic field times V cross R divided by R squared. Again, R hat, that's a unit vector in the direction of the position vector from the charge to the point of interest. So if this is vector R right there, we can make that into a vector R. And then this here would be the unit vector, like so. And then the charges here are causing magnetic field there. By the way, direction-wise, if you use your right-hand rule, you point your fingers in the direction of the thumb, and you point your thumb in the direction of the current, and your fingers will point in the direction of the magnetic field. Notice that it's a circular, or the magnetic field goes around in a circle around the wire, and to the right of the wire, the magnetic field is into the board. So let's just indicate that the magnetic field here will be into the board. Now, since the magnetic field here is not caused by a point charge, but by a small line segment, we have to make an adjustment to the equation. So the small amount of magnetic field here is going to be caused by the small amount of wire, so we're going to call that a dB, and that is equal to mu sub naught divided by 4 pi. And instead of q times v, we're going to call that I times dy multiplied times the directional vector r divided by r squared. So q times v is the same as I times dy. If you say, well, why is that so? Well, quickly, we can say that I, by definition, is equal to dq dt, or, simply said, the amount of charge passing by in a given amount of dt. And then v can be defined as dx dt, or in this case, since we're moving in a vertical direction here, we can call it dy dt. So this is dy dt. And if I then write q times v, I can write, just a moment here, so if I write q times v, that can be replaced by, let's see here, q times dy dt. And if I take my dt and put it underneath the q, I can say that this q divided by dt times dy, and q times dt is equal to I, so this is equal to I times dy. So you can see that q times v can be written as I times dy, which is what I did over there. All right, next thing we need to do is replace r squared by what r squared is equal to. So this can be written, dB, can be written as mu sub naught divided by 4 pi times I times dy cross r divided by r squared, and r squared is equal to big R squared plus y squared. All right, we're almost there. So dy is the small little dy right here. The r vector, that is the unit vector in this direction, and we have an angle between them here, which is theta. Now, we can say that 180 degrees minus theta, and if we take the sine of that, let me rewrite it again. So if I take the sine of this angle right here, the sine of theta is the same as the sine of 180 degrees minus theta. And this here is 180 degrees minus theta. So if I take this angle here, 180 degrees minus theta, or this angle here, theta, it's the same thing. So this can now be replaced by the angle theta. And if I look at this triangle, this is the opposite side to theta, this is the adjacent side to theta, I can then say that the sine of theta is equal, by definition, to the opposite side over the hypotenuse. And in this case, the opposite side is r, and the hypotenuse is little r right there. So this is the opposite side to the angle, this is a hypotenuse, little r. And so then if I rewrite this right here, I can say this is equal to, dB is equal to mu sub naught divided by 4 pi times I, and instead of dy times r, I'm going to write dy, the magnitude of dy times the magnitude of r, and of course it's a unit vector, so that's just simply 1, times the sine of the angle theta. And then divided by r squared plus y squared. And then I can see that the sine of theta can be written as big R over little r. And since little r is equal to the square root of r squared plus y squared, that looks pretty good right here. So we can say dB is equal to mu sub naught divided by 4 pi times I times dy. And instead of the sine of theta, I'm going to write big R divided by little r. And little r is r squared plus y squared to the 1/2 power. It's the square root of this, like that. Then I can combine all that and finally write that dB is equal to mu sub naught divided by 4 pi times I times r divided by the quantity r squared plus y squared to the 3/2 power. Okay, now that's the contribution to the magnetic field here by this little line segment, expressed in terms of the current, the distance away from the wire, and the distance away from the midpoint right here. And I'm missing my dy. Can't do that. There we go, dy. All right, now we have to integrate that over all the little line segments. What we're going to do is we're going to integrate from 0 to a and double it, because this line segment will give it the exact same contribution as this line segment. So to find the total magnetic field B, and of course we're looking for the magnitude here because we already found the direction. So the magnitude of B is equal to twice the integral of dB from, and I guess I want to magnitude that out only, from 0 to a, which is equal to twice the integral from 0 to a of this quantity right here, which is mu sub naught I times r over 4 pi. Those are actually constants. So mu sub naught times I times r over 4 pi, which eventually will go outside the integral sign, times the integral of dy over r squared plus y squared to the 3/2 power. So moving everything out of the integral sign that doesn't need to be there, all the constants. So this is equal to, and of course this 2 cancels out this 4, so we have mu sub naught times I times r divided by 2 pi times the integral from 0 to a of dy divided by r squared plus y squared to the 3/2 power. Now that's a rather difficult integral. We can use trigonometric substitution or simply just go to a table of integrals, and when we integrate that we get the following. This is equal to mu sub naught I r over 2 pi times the quantity. We have y divided by r squared times r squared plus y squared to the 1/2 power evaluated from 0 to a. Okay, now you notice that this r will cancel out one of those, so this cancels out one of those r's. And now we go ahead and evaluate that when we plug in the upper limit. So this is equal to mu sub naught I over 2 pi. When we plug in the upper limit, we get a divided by r times r squared plus, instead of y, we're going to substitute y, so this is a squared to the 1/2 power minus when we plug in the lower limit. Now notice when we plug in the lower limit, when we plug 0 in the numerator, that goes to 0. So that disappears. So ultimately, the strength of the magnetic field at a distance r away from a line segment that has a length of 2a is equal to mu sub naught times I divided by 2 pi times the quantity a divided by r times r squared plus a squared to the 1/2 power. All right.
இப்போ ஒரு current element வந்து find the magnetic field at a point at a distance r away from a wire of length 2a carrying a current I அப்படின்னு சொல்றாங்க. ஒரு current carrying wireல I என்ற current போறப்போ அதிலிருந்து நம்ம என்ன செய்யறோம்னாக்க ஒரு குறிப்பிட்ட டிஸ்டன்ஸ் இருக்கக்கூடிய பாயிண்ட்ல இருக்கக்கூடிய மேக்னெட்டிக் ஃபீல்டோட வேல்யூ கண்டுபிடிக்கிறோம். முதல்ல பைட்-சாவர்ட் லாவினுடைய ஐடியல் கிராஸ் ஆர் வடிவத்தை எடுத்துக்கிறோம். பொசிஷன் வெக்டர் கால்குலேட் பண்றோம், ஆங்கிள் கால்குலேட் பண்றோம், இன்டகிரேட் பண்றோம், டிஎல் இருந்து இன்டகிரேட் பண்ணி அதனுடைய வேல்யூவை கண்டுபிடிச்சிருப்போம். சப்ஸ்டிட்யூட் பண்ணி we are really going to find out the value.
Now, what if you have an infinitely long wire? What if A becomes really large, infinitely large? Well, if A becomes infinitely large, then A is going to be much, much larger than R. And so basically we can eliminate R from inside this radical right here. This is to the 1/2 power. So we can say if A is much, much larger than R, this then will become approximately equal to mu sub naught times I divided by 2 pi times A divided by R times A squared to the 1/2 power, because a very big number squared plus a very small number squared is basically equal to the very big number squared. And then you can see that A squared to the 1/2 power is the same as A, so this can now be written as mu sub naught I over 2 pi times A over R times A. And of course, this A will cancel out that A, and this then becomes equal to mu sub naught I divided by 2 pi R. And that is equal to the magnetic field due to an infinitely long line segment or a very long line segment. As long as the line here is much, much larger than the distance from the current carrying wire to the point of interest, That's the equation we'll use for the magnetic field. So either we will use this equation right here for a very long segment of wire, or we'll use this equation right here for a short segment of wire, where the segment is equal to 2a.
அதாவது கொடுக்கப்பட்டிருக்கக்கூடிய வயருடைய லெங்த் வந்து இன்ஃபைனட்டா இருந்ததுனாக்க தான் மியூ நாட் ஐ பை 2πr யூஸ் பண்ண முடியும். ஆனா ஃபைனைட் டிஸ்டன்சஸ் கொடுத்துட்டாக்க நம்ம வந்து முதல் ஃபார்முலாவை தான் யூஸ் பண்ண முடியும். அதான் அவர் இன்ஸ்ட்ரக்ட் பண்றாரு.
In length and the distance r away from the wire. All right, now that we have those two equations, we can now solve some problems by finding the amount of current or the amount of magnetic field that we have next to a current carrying wire. So let's go ahead and do some examples there. Welcome to our lecture online, and here's a straightforward example of how we apply the equation that we found in the previous example on something like this. So assume that you have two parallel wires, one that carries a current upward, the other one that carries a current downward, assuming the wires are infinitely long relative to the distance away from the wire. What is the magnetic field at this location, 30 centimeters to the right of the second wire, if the two wires are 20 centimeters apart, and the current upward in the first wire is 5 amps, and the current coming down in the second wire is 10 amps. So how do you go about doing that? Well, what we're going to find here is that the magnetic field here is going to be a vector sum of the magnetic field caused by the first wire and the magnetic field caused by the second wire. So let's first find the direction of the magnetic field caused by each wire at that location. And I'm looking for my red pen here. Here it is. So using the right-hand rule, if the current goes up in the first wire, I use my thumb to represent the current going up. Then my fingers curl in the direction of magnetic field. So to the right, the magnetic field will be into the board due to the first wire. So I can say into the board right here, and that would be due to B1, meaning the magnetic field caused by wire 1. Looking at the second wire, I can see that the current goes down. I use my thumb in the direction of the current. My fingers curl around in the direction of magnetic field. So to the right of this wire, the magnetic field will come out of the board. And let me use a different color here to indicate that. So here we have the magnetic field coming out of the board due to the second wire, so I'll call that B2. Now, if the magnitude of B2 is larger than the magnitude of B1, then of course the net magnetic field will be out of the board. If the magnitude of B1 is larger than the magnitude of B2, then the net magnetic field will be into the board. So let's find the magnitude of each of the magnetic fields to figure out what the net magnetic field will be. So the next step is to find the magnitude of each wire. So B1 is equal to, we're looking for the magnitude of B1, and the equation is mu sub naught divided by 2 pi times the strength of the current divided by the distance away from the wire. Now, this point right here is this far away from wire number 1. We call this distance R1, and that's going to be 20 centimeters plus 30 centimeters, or 50 centimeters. So plugging in the units, this is equal to 4 pi times 10 to the minus 7 Tesla meters per amps. Multiply times the current. The current is 5 amps. And we divide that by 2 pi times R1, and R1 is 0.5 meters. All right, using my calculator and simplifying things a little bit, the 2 pi and the 4 pi cancel like so, and then of course amps and amps cancel, and meters cancel, so you end up with Teslas. So we have 2e to the 7 minus times 5 divided by 0.5 equals, and it's 2 times 10 to the minus 6. So this is equal to 2 times 10 to the minus 6 Teslas. Now doing the same for the second wire, the magnitude of the magnetic field caused by the second wire is mu sub naught I2 divided by 2 pi times R2. So again, this is 4 pi times 10 to the minus 7 Teslas meters per amps. Multiply that times the current in the second wire, which is 10 amps. And dividing that by 2 pi times R2, and R2 is the distance from the second wire to the point of interest, which is 30 centimeters, which is 0.3 meters. And again, amps cancels out amps, meters cancels out meters, and you get the following. And of course, this cancels out with that. That becomes 2. So we get 2 e to the 7 minus times 10 divided by 0.3 equals, and it's 6.67 times 10 to the minus 6. 6 times, or 6.67, 6.67 times 10 to the minus 6 Teslas. Now notice the magnitude of the magnetic field caused by the second wire is much larger than the magnitude of the magnetic field caused by the first wire. So the net magnetic field direction will be in the same direction as the larger portion of the magnetic field. And so we can now say that the total, B2, or B total, is simply equal to the sum of B1 plus B2. Now notice that B1 is into the board, let's call that negative. B2 is out of the board, let's call that positive. So this is equal to B1 into the board, that would be a minus 2 times 10 to the minus 6 Teslas. Let's call that the z direction, right? If this is y and this is x, so call that the z direction. So in the negative z direction, plus 6.67 times 10 to the minus 6 Teslas. And let's call that in the positive z direction. So the sum of those two would be 4.67 times 10 to the minus 6 Teslas in the z direction, and that would be the result.
ரெண்டு வயர்ல கரண்ட் போகுது, ஒரு வயர்ல 5 ஆம்பியர் போகுது, இன்னொரு வயர்ல 10 ஆம்பியர் போகுது. ரெண்டு பேரலா இருக்கு, ரெண்டுமே இன்ஃபைனைட் கண்டக்டர். அதுல இருந்து 30 சென்டிமீட்டர் தொலைவில் இருக்கக்கூடிய பாயிண்ட்ல மேக்னெட்டிக் ஃபீல்ட் என்னன்னு கேக்குறாங்க. முதல் வயர்ல இருந்து பாயிண்ட் ஆஃப் அப்சர்வேஷன் 50 சென்டிமீட்டர் இருக்கு, ரெண்டாவது வயர் 30 சென்டிமீட்டர் இருக்கு. ரெண்டு ஃபீல்டு கால்குலேட் பண்ணா B1 B2 வேல்யூ கால்குலேட் பண்ணிக்கலாம். B1 உடைய டைரக்ஷனை கால்குலேட் பண்ணோம்னாக்க ரைட் ஹேண்ட் தம்ப் ரூல்ல கால்குலேட் பண்ணோம்னா அது இன்சைடா இருக்கு, ரெண்டாவது ஃபீல்ட் அவுட் சைடா இருக்கு. நெட் ரிசல்டன்ட் ஃபீல்ட போட்டு பார்த்தோம்னாக்க B1 பிளஸ் B2ல B1 இன்சைடா இருக்கிறதுனால மைனஸ், B2 அவுட் சைடா இருக்கிறதுனால பாசிட்டிவ். நெட் ரிசல்டன்ட் ஃபீல்டுக்கு வேல்யூ வந்து
of adding those two vector quantities together. All right, again, recapping real quickly. We had two wires side by side, one carrying a current up, the other one carrying a current down. Each one of these wires will contribute some magnetic field at that location. First, finding the direction of each, we notice that if the current goes up, the magnetic field will be into the board to the right. If the current comes down, the magnetic field will be out of the board to the right of that wire. Then you find the magnitude of the contribution of each of the magnetic fields from the two wires. You add them together, realizing that one is into the board, we'll call that negative. The one is out of the board, we'll call that positive. When you add them together, you get the total magnetic field right there. All right.
Okay, தொடர்ந்து பார்க்கலாம்.